Let's find out which horizontal velocity and vertical velocity graph is fit with the scenario given in the question. Okay, so the question says that at the time t is equal to 0 in a classroom, a sphere is thrown vertically, not vertically, is thrown at angle 45 degrees to the horizontal, and at this time t1, important point is that it bounces off how elastically, which means that it will bounce with the same speed with no friction. So which one of these are the correct horizontal and vertical velocity graph with respect to time? Okay, now if we try to draw the situation that what they are trying to say, so let's say this ball is thrown at an angle 45, and what will be its trajectory? So it should be, the ball will go like this. So at this point where it is bouncing, at this point, this is a velocity. This is a direction of the velocity. Okay, so it will bounce back because it is colliding elastically. So this will be the same speed. And that's why how the ball will move then. The ball will bounce back like this and then move in this curved path due to the gravity. Now, if we see the ball's position at the different instant of time, so the ball's horizontal velocity will not change. Okay, if this is angle theta, that's 45, so this horizontal velocity will be same, that is v0 cos of theta, right? Remember that it will not change, right, till this time. What will happen after the collision? Because it's collided elastically, that's why even after the collision as well, the velocity along x-axis is still same. Okay, why is same? Because angle is not changed. So that at the time, at the point of collision, it's a elastic collision. So if the ball was coming like this, imagine, so this is a theta angle of incidence and this is the angle of reflection, right? Both angles are same, so angle is not changed, velocity has not changed during the collision. That's why we must draw the horizontal velocity time graph like this. Not even at the time t when you see there's a no change. So that's why it's either the answer A or B. So it means both of these answers are not possible. So you know that we are considering it as a free fall motion. There's a no air resistance. That's why we are saying the horizontal velocity is not changing. Okay. But what about the vertical velocity? In absence of air resistance, the vertical velocity changes something like this, right? Starting from its maximum value, v0 sine theta. Okay. And then it decreases like this. It becomes zero in the general situation, but as you see at this point, it is hitting. At this point it is colliding elastically. That's why it will still have some velocity at the point of collision. And if you see that, if I make the components, right, so then we see that this is a vertical component, this is a velocity before hitting, right, and this is a vertical component just before hitting. It means that this vertical component was changing overall, right? It was changing and it is, by the way, decreasing, which means that actually it will decrease, but it will not be zero, right? Before hitting, it has some value still, right, at the time t1. What happened at the time t1? When it collided, now you see this one arrow. Okay, I draw it again. I draw it again for you. This is an arrow which is representing the same speed. Okay, you see that what is the direction of its vertical component? That is downward, and it is, by the way, same as the red one. Okay, so that's why, so exactly at the time t1 when it collided, it has now a negative value of vertical velocity, which I had shown you with the help of green arrow when I zoomed in this screen. Okay, and then what will happen now? At all the instants, now you see that the vertical component of velocity is negative because that's downward. That's why now it will increase. But how it will increase? By the same rate. So this should be the vertical velocity graph. So on the basis of this information, the right answer must be the option B.